Hi, in this lecture we are going to be seeing an example for using decision trees in Python to classify the iris data set. So techniques we would be using are decision trees, splitting into training and testing, and also using confusion matrix. So the data set we are going to be having for this exercise is the iris data set, which basically consists of three types of flowers: Setosa, versicolor, and virginica. And for each of the flowers, there are a number of samples, basically samples taken from various flowers. And then for each of the sample, you have measurements of the petal length, petal width, sepal length, and sepal width. And the idea is that we are going to be building a model which can predict the type of the flower just by knowing the sepal length, sepal width, petal length, and petal width. So we will be building a model to predict the type of the flower. And let us start this one by first loading up all the libraries you need for both pandas and scikit-learn. And then switching over to your home directory for this exercise, doing the os.changedir. Then we go to loading the data set. So I'm going to be loading the iris.csv, which is available to you in your resource bundle. Once I load, let me take a look at the data sets that are there. So D types, so sepal length, width, petal width, all of them are float 64. Okay, they are all numbers. Good. Species is an object. Good. Then let's look at the describe one and see how the various things are ranging. So sepal length is anywhere between 5.84 to 7.9. Sepal width from 3.05 to 4.4. And these values all look pretty decent. There is nothing to be worried about it. There doesn't seem to be any kind of outliers in the data, so we are kind of fine. Let us also take a peek at the data by doing the head command. And this is how each record looks like, and the species is actually shown in the end. Once we do this, let us start doing some exploratory data analysis. Let us start by looking into how these variables are related to each other. So first thing, I'm going to be plotting this petal length against the petal width. And let us see how that one comes up as the petal length against the petal width. Okay, and let us see this chart. You see that something interesting: as the petal length increases, the petal width also increases at the same time in like a very close manner. Okay, let me just draw it 1 second for you. Okay, here it is. So as the petal length increases, the petal width also increases at the same time. So you see that almost it follows a diagonal straight line, which shows that petal length and petal width are highly correlated to each other. So two feature variables here are very highly correlated with each other themselves. You can even say that I can eliminate one of them if I need to and still do my predictions. The next thing I'm going to be doing is sepal length and sepal width. So last time we did the petal part, now we are doing the sepal part. And this you see is kind of distributed all over the place. So the sepal length and sepal width does not seem to have a good relationship. The points are all over the place. For a given value of sepal length, the width can anywhere be ranging from 2.0 to 4.5. So there's not a lot of good relationship between the features. Ideally there should be no relationship between the features. So this is kind of okay, good. The next I'm going to be doing is a box plot of petal length for each of the type of the species. So I'm going to be doing a box plot for petal length for Setosa, for versicolor, and virginia as three different plots. And let's look at how that one comes up as. This is petal length. So start off with petal length. You see that for the different types of flowers, the petal length is totally distinct from each other. What that means is, just by looking at the petal length, I can say it is Setosa. There's high predictability in petal length. So the petal length is something like 1.5. I know it is Setosa because you see the range of versicolor is somewhere here between 3.5 to 5.5. And for virginica, it is somewhere between 4 to 5. So it's very easy to say Setosa has very uniqueness. Just by looking at the petal length, I can say, okay, this is going to be Setosa. Let's do the next one, which is the petal width, and see how it comes up. Petal width, similar patterns. Very similar to petal length. We saw first of all petal length and width themselves are highly correlated to each other. Now you see that they both are highly correlated with the type of the flower. Then we go to and look at sepal length. Sepal length, let us see how it looks like. You see a similar pattern, but they're not that distinct. They're high. There is a lot of overlap. The overlap in terms of the sepal length between setosa and versicolor, there is some lot of overlap. So you can't really say just by looking at sepal length I can say, okay, this is going to be setosa or versicolor. So you can see the ranges are higher, but still there are a lot of overlaps here. Let's look at sepal width then. In sepal width, you see that it's all over the place. Now you see that setosa sepal width has gone higher, versicolor has gone lower, Virginia is somewhere in the middle. Still a lot of overlap between the values, so I can't just look at sepal length and say, okay, sepal width and say, okay, this is going to be of this flower type. So there's a lot of overlap when you look at them. Petal length, petal width had very distinct values. Sepal length had medium level of distinct values, and sepal width not so much. So that's the kind of finding you have in terms of a correlation. This is correlation analysis by looking at the charts. Now let's do an actual correlation analysis by calling the irisdata.car and see what that correlation analysis tells you. Pretty much you see something that we noticed here, the petal length and petal width. They have high correlation with each other. Though this one you see is 0.96. So petal length and petal width have really high correlation with each other. Sepal length not so much. Petal length and petal width seem to be the ones that are highly correlated to each other. This is not showing the correlation for the type of the flower. If you wanted, we could have converted them as numeric values and still done the correlation for them also. But we kind of saw what the correlation is by just looking at the box plots, right? So that is usually kind of enough. Okay, moving on. Once you do the correlation, let us go and try to do the split of the training and testing data sets. So we kind of did the same exercise in linear regression. We're going to repeat it again. We first split the predictors and the targets into separate variables. So predictors being sepal length, sepal width, petal length, and petal width, and the target being the species. Now it is split. Now then we call the train test splits function with input as predictors and targets, and the ratio is 70:30. Again do the training and test split. And then you see, look at all the shapes that are there. So you can look at all the shapes, and you see that there are 150 records in the original data set. It got split into 105 and 45. So this is kind of what you have come up with. The process is kind of, as you see, repeating. This is the same process that will repeat for any classification exercise. Once the training and testing set is split, let's now start initializing the decision tree classifier. So you open the classifier decision tree from scikit-learn, and then you call classifier.fit. Fit is the learning process to which you pass the training predictors and training targets. Once you pass, it is going to build a model. Now this one, now you see it instantaneously comes back. If the data is huge, this particular process might take a long time to run, even hours in case there are millions of records in there. Then you do the predict function, which is you're predicting for the test values. So you pass the predictor test data set, and then you're trying to make a prediction of the target test set. So you're doing the prediction. Now the predictions come out. There should be about 45 predictions, one for each of the record in the predictor data set. Once you do that, the sklearn matrix has confusion matrix as a function. So you can call the confusion matrix function and pass the target test and predictions. The target test is the actual values that you're trying to predict, and predictions are the predicted values. So let's see how the predicted and actuals work against each other by calling the confusion matrix. The confusion matrix, as you can see, it shows here on the top. The columns are the setosa, versicolor, Virginia. The rows again are setosa, versicolor, Virginia. The diagonal actually shows you all the right predictions because you're predicting each as itself. Diagonal is all the right predictions. If you have questions on confusion matrix, please go back to the lecture on confusion matrix in the presentations. The diagonal is all the right predictions, all the true positives, and then the errors are the ones that are showing up around them. So there's only predicted one of them incorrectly, that is this one. Otherwise, all of them are correct, and that is expected because we saw that sepal length and sepal width had really high predictability. You can also look at the accuracy score for this. Again, sklearn metrics has a function called accuracy score, to which you pass the target test and the predicted value and the actual predictions, and that gives you an accuracy of 0.97 or 97% accurate. And then you can also do a classification report on it and look at them too. So this is how you do decision tree classifier. Now the next question is, how do I take a peek at what is the decision tree that has been built? Now let's take a look at the decision tree that has been built, and for that we are going to be using a library which is called a tree library and do some stuff on them to get the tree out. So this is the steps you have to do to get the tree out. You import a bunch of stuff here, and then you take the string IO, and based on that you build the tree wizard, and then finally use PyDot to actually build a graph, and then you also plot the graph. So this is the graph that got built. This is the actual decision tree that it has built. So what is the decision tree? Let us take a look. And at the top of the decision tree it says x of 3. X of 3 means it is the fourth in the list of predictors. The predictors that you actually passed for it are sepal length, sepal width, petal length, and petal width. So x of 3 is nothing but the petal width. So it is starting off with petal width. With petal width less than 0.7, it goes into this one, which is going to go into this one, which is 32. So when it said 3200, it means it says that 32 of these are Setosa, 0 versicolor, 0 Virginia. But if it is not, the 105 samples got split as 32 and 73 based on this x of 3 decision. So the first decision is x of 3 less than 0.7, or the petal width less than 0.7 means it is going this way and saying all of them are Setosa here. Then, or the x of 3, if it is greater than 0.7, then you make a second decision, which is x of 2. X of 2 is the third variable, which is the petal length. So sepal, this is 0, 1, 2, 3. So x of 2 is going to be petal length. If petal length is less than 4.85, then you make further decisions, again on x of 3, again on x of 3. So the tree keeps building, going as we go down, and finally at all the root nodes you see that you finally decided upon what is your final answer. So you see that value equal to 3200, which means all of them in this case are the first type. Or if we go and look at here, all of them here are the second type, 0, 30, all of them are 30th second type. Here all of them are the third type. So it's a big tree it has built to kind of fully classify the data and predict based on the various values you have passed. And we saw this accuracy is 0.97%. And the accuracy is so high simply because we found that petal length and petal width, which is what are the top variables that you used in the tree, so petal length and petal width, are highly predicting variables. So what happens if you don't have petal length and petal width? How will the decision tree work? Without petal length and petal width, how is the accuracy of the decision tree that will be built? So for that, what we are going to be doing is we're just going to be taking sepal length and sepal width alone and use that as the predictor variable. Now repeat the entire process and see how the tree looks like. So we just take sepal length and sepal width alone and repeat the entire process of classifier, building, testing, and then looking at the confusion matrix. So I'm just going to run all of them in one shot here. So now you look at the confusion matrix, you see a lot of errors. So this is an error, the 9 is an error, the 10 is an error, 1 is an error, because they are not predicted correctly. Only the ones in the diagonal are predicted correctly. And now let us look at the accuracy score here. It's only 0.55. So earlier we had an accuracy score of 0.97. By removing two of the highest predicting feature variables, it came down to 0.55. So this kind of explains how the correlation between the predictors and the actual and the predicted value affects the overall prediction. So when your variables have high signal, high correlation with the target, your predictions are high. If the variables do not have high correlation, your predictions are going to be low. And this is how your decision tree works. So decision tree is one of the simplest algorithms to use, As you can see, you can draw the decision tree and show people this is how the actual decision tree took its decisions. You can actually see the decision making process in the decision tree. And it is an explainable model, easily explainable to anybody. And it is also a fast model, but it is prone to having very bad accuracy ratios. In our case, the data had very good signals, so it predicted very well. But if it did not have very good signals, the decision trees will have very poor accuracy. So much for the decision trees. Thank you.